say, for example, this is zone, and this is the normal tool.
The log for the
Yes.
cross entropy.
Log axis.
The log for the cross entropy, my
Yes.
friend.
Yes.
It's the log for the cross entropy
Oh yes. So
objective function.
yes, and why we just multiple, for example, 100? Like this, maybe.
Well, if you do that for that, you're going to have to do the same thing for the log, right?
But why? So why you say this is better than this? I can multiple 100.
Well, if you multiply x by 100, you have to do the same thing for the
No.
cross entropy
No,
function.
I don't need to do it.
Right? Okay, I tell you what. Why don't you think about that, and tomorrow you have a chance to. So I want to finish up. So, remarkably, the cross entropy seems like for the labs you're going to be doing, and for a lot of people in literature, for at least binary classification, is the preferred way to go. And this is a pseudo explanation of it, although this guy's going to try to refute that tomorrow morning. Okay. Notice I'm very careful with my wording. Suggest doesn't prove, it just suggests this is true. Oh, now what if you have, now this is one experiment, one photograph. What if you have more than one photograph? How do you bring in the other photographs into our objective function? Look, man.
I don't know.
Okay, well, I don't blame you. But in the context of other photographs, this is photograph number 1, photograph number 2, and each of them had a class, and Lou and Marco knows that if these are independent random variables, that is, there's no correlation between the two, you can break this up into a product of the individual conditional probabilities. Okay. And if you take the logarithm of both sides there and put a minus sign, that's how you incorporate the extra photographs. And the logarithm of a product of functions is what? Look, man. Log of A times B is what? Look, man.
B.
Log A plus log B.
B. Log of A times B is
summation.
what?
It will be summation
Of what?
of
Log A and log
if
B.
it's log A plus B, it will be A plus B. It will be summation
I think-
of all the probabilities here.
Okay, so you got it, okay? So it'll be just the sum of all those puppies, and that's what that is, okay? Instead of a product. And that's what Abdul is going to do. Abdul is going to take a derivative of one of these guys and tell us what it looks like. Okay, and this is what he's going to do. I'm going to go through this. The epsilon dw. Notice that epsilon is his new friend for one photograph. He's going to go through this stuff with the chain rule in detail. And lo and behold, what's he going to get? He's going to get residual times x. That is x transpose times residual. Just like you got in the least squares situation. Wow, what a surprise. But he's going to show us.
And that's if we take the derivative. If we take a derivative, we'll get a residual times x.
You're just going to prove it tomorrow. First thing, before class starts tomorrow, you're going to come in. Okay,
Right.
so now we just use his old code he wrote down yesterday, x transpose times residual times the step length. Bingo.
Okay.
Okay. Before, with the least squares, you had this extra term here. What was the extra term again in terms of A, Abdullah?
In the least square?
Yeah, and you had that hump, okay? What's the formation? What's the form of that?
Transpose, you mean? The
A
matrix.
times 1 minus A, right?
A times 1. Yes. Yeah. Which one is it? A times.
Okay. This is the same as least squares.
Okay.
Wow, this is even easier. Abdullah likes things easy.
Everyone likes easy.
And then if you want to add up all the photographs, the gradient contributions from all the photographs, you just okay. There you go. So simple. 4 lines of MATLAB to your neural network, or at least one network. Okay, I don't think we need to do this. This is what Abdullah wrote down, except now he has instead of a misfit function, there's an objective function. This is iteration, and this is just going to the algebra of implementing this guy. And we want to do batch processing. So what do we do with batch processing? This is a stochastic gradient. Notice there's no one photograph, right? So one photograph here, X. That's stochastic gradient. We want batch gradient. What are we going to do to the code, Abdullah?
What do you mean by batch processing?
Oh,
It's
Lee,
like-
tell them what batch gradient is.
I know what's batch gradient,
I mean,
but
it's for-
processing is
Same thing.
okay. So basically, it makes the code takes the whole data instead of
Yeah, instead of
just the whole.
you did a stochastic gradient, you're only using one photograph, and that since this misfit is a result of all the photographs. That one photograph you're using may do something like that for the gradient. But if you do all the photographs, you get a gradient like that, a gradient like that. And then you add all this stuff together, the erroneous gradients are going to cancel one another out, or hopefully. And you'll get someplace that when you add them all together. So that's batch processing. This is stochastic gradient. And you can feed them in one photo at a time, different colors, different photos. And that's just figure that out yourself. So in summary, what we talked about today was how to do your first neural network code. There's an I here. I did in the context of classifying our photos. And here's a rule of thumb. Oh, what did we forget here? What's the best practices for neural networks? Remember, there's something we do to the input data.
You normalize it.
Normalize it.
Or demean it.
And or demean it?
I mean, demean it and normalize
Yeah,
it.
demean it and normalize it. So I'll go between, say, 0, -1 and 1, so all the input values. Okay? You don't put these in as they stand. But another thing, another best practices is your input W's. You always need a starting model, right?
No. So they use
Random,
a
a random starting model that between -1 and 1 so, for the slopes. Now, I haven't put explicitly in calculating the B's, but that's something we'll be looking to do later. And then we just go ahead and do this. So I should put a normalization to mean. Okay, we also looked at the cross-entropy function. And what exactly is this cross-entropy function trying to do? It's trying to find the W. And as we're going to find out later when we look at support vector machines, we have a cloud of points, and the red motorcycles are here, and the green motorcycles are there. I should put W2, W1 there. I should put red versus. So you're trying to find a line that separates the two classes. And a line is described by a B, an intercept, and a slope, W. It turns out that this is what this is trying to do. Find a straight line with a special slope that will separate out the green from the red. Is that possible here? Abdullah,
You want to separate the green?
from the red. Can you find a straight line that can do that?
I know we have one red there. No, there is no straight.
Yeah, it's good to try. Yeah, you just can't do it. Okay.
How you need to push some.
So you have an inconsistent set of equations. Support vector machines is going to be a very efficient way to do this. Now, one thing I haven't mentioned is, what about multi-class? That is, instead of one output, 1 or 0 here, we can have multiple outputs. And if it's a cat, it'll be a 1 here. If it's a dog, it'll be a 1 here. And zeros everywhere else. If it's a mouse, it'll be a 1 here, and so on. Well, in that case, this guy, Z1, you hit it with
Softmax or
is what we call softmax. And this is like a probability function. And when I get to the days of rigorous theory, I'll relate this very carefully to a conditional probability function. So this goes between the values of, oh, these should be a plus. This goes between 0 and 1, so it's like a probability function. And I'll show later in the course that this is like, if you have an input X, what's the different classes? Okay, probability of the different classes. Okay, so I was just talking about that. Oh, you lied, Abdullah. There is a line that separates the two.
this
Okay.
is different.
Okay, so I'll see you tomorrow at noon. How many are coming tomorrow? Because we could order lunch for you guys. If Abdullah brings lunch.
No.
We'll pay you. We'll pay you back.
I should bring the lunch.
From Subway.
Okay.
Oh, wait a minute, we can't because it's in the lab.
They're not allowed to.
So try to eat lunch beforehand.
So,
Okay, try to